Hi everyone, we're Group 29 and our project is fault-tolerant design of passive biomedical implants.
I'm Jack O'Connor, and I'm an electrical engineering student with about 2 years of experience in aerospace manufacturing, including diagnostics and quality assurance.
I'm Divita Rajmohan and I'm a senior in electrical engineering.
I'm Joshua Ravello, and I'm an electrical engineering student at ASU in hardware design.
I'm Julian Gervassi-Saga. I'm an electrical engineering student at ASU in semiconductor research.
My name is Rachel Hayes. Current biomedical implants rely on internal batteries that require invasive surgical replacement once depleted. Surgical interventions carry risks including infection, tissue damage, and prolonged recovery. Ongoing research is focused on wireless batteryless implants that harvest energy remotely. Reliability remains a challenge, as minor faults, like failed capacitors and degraded connections, can cause complete system failure. Without fault tolerance, a batteryless implantable systems cannot be safely or practically deployed in clinical settings.
Active to active redundancy is going to be placing backup subcircuits in parallel, sharing the load, while active to passive is going to be switching in and out of active mode, the backup subcircuits. Active passive is better when you have more precise analog values you have to maintain, such as an RC time constant. Now, another factor to consider in a flex circuit especially is mechanical stress. If you reduce footprint sizes, you reduce the chances of connection breaks.
For our design, we adapted a cardiac stimulator circuit developed by Dr. Jennifer Blaine's group. We introduced active-active redundancy, also known as parallelism, in the voltage multiplier stage, and developed active-passive redundancy, also known as an external switching mechanism for an RC gate timer. This is necessary since a gate timer's time constant is highly sensitive to faults. This selective switching approach allows for a faulty gate timer to be bypassed, preserving the circuit function without the need for surgical replacement.
This slide highlights the results of our fault injection test on the energy harvester. We focused on open circuit defects, which simulate broken connections in the circuit. In the top left graph, we see that as the number of defects increases, the output voltage drops sharply. However, the graph on the right shows that by adding parallel capacitor redundancy, we significantly improve stability even with four faults. The bottom wave shows our RC gate timer in action using analog pulses to control switching. Overall, our design maintains strong performance and resilience even under fault conditions.
Our redesigned device reduces the need for surgical intervention by enabling fault recovery without requiring physical access to the implant, meaning the recipient will undergo fewer invasive surgeries and therefore be exposed to fewer associated risks. This solution enhances the long-term reliability of wireless batteryless implants through built-in fault-tolerant mechanisms. Without fault tolerance, implantable devices are limited in their long-term viability, resulting in increased healthcare expenses and diminished patient quality of life.